Hello and welcome to Lecture 13. This is our introduction to quantum physics. In this lecture, we're going to introduce the duality of light to extend our understanding that we picked up last week. After that, we'll have to introduce the principles that lead to quantum theory, which will allow us to investigate the applications of quantum physics. We'll look through extending our understanding of quantum physics. With that, we'll introduce Beer's law and also look at the Compton effect and the experiments that allowed the expansion of quantum theory. We'll finish by investigating several of the different applications to spectroscopy, looking at the ways we use our knowledge of quantum physics to better understand the substances we are investigating. In the previous lecture, we examined the wave-like behavior of light, and physicists have done experiments that have let them observe that behavior. But they've also observed behavior that can only be explained by light acting as a particle. The merging of these two concepts is the domain of quantum physics. So we've seen the wave-like behavior, where light comes in with a wavelength and a frequency and a wave speed of the speed of light. And this behavior can explain concepts like refraction and diffraction and interference. And this allows us to consider energy transfer in very classical terms, which is the way we've seen before about you can continue to add more and more and more energy to an object. And with these experiments, we always see energy transfer with continuous values. So we can send 1 joule or 1 1/10 of a joule or 1 100th of a joule or 1 1,000th of a joule. We can always make smaller and smaller cuts of our energy into different levels. The particle behavior of light is slightly different. So in the particle behavior, we see light move as one small unit. There is a minimum quantity of energy transfer, and we can't transfer any smaller amount of that. So we can either transfer one quantity or two quantities, but we can't transfer 1 1/10 of a quantity. The other way to talk about this is to say that the values are discrete, so they only take on integer or whole numbers. And this is where we get the quantum part, and you want to think quantum connects to minimum quantity. That minimum packet of energy is referred to as a photon. So we're going to shift our focus now to photon energy. A physicist, Max Planck, was able to derive an equation to predict this energy level that a photon carries, and it was able to use that by considering the wave nature and particle nature of light. So remember that we're going to define photon as a packet of energy that's associated with light. I tend to use this circle with a squiggly line in it to represent a photon moving, so we recognize the difference between it and an electron or a proton. And Max Planck's equation is that the energy of a photon will be equal to h times f, where f is the frequency associated with the wave of light. So any photon, even though it behaves like a single particle, is still associated with a wavelength of light. Remember, the wavelength determines the color and energy level of light. And the other piece of information in that equation is h, which is Planck's constant. For our course, it'll be precise enough to look at Planck's constant as 6.63 times 10 raised to the negative 34, and it brings with it units of joules seconds. I know many of you are reading outside of the course, so some other textbooks represent this equation as E is equal to h times this odd symbol that looks like a V, and it's the Greek letter nu. With this consideration of energy, we need to consider a new unit. We're going to consider the electron volt. So an electron volt measures the exact same quantity as joules, and they can be converted back and forth. So a 1 electron volt has been set as 1.602176,634 times 10 to the negative 19 joules. You may recognize this value as it is very closely related to the amount of charge on an electron, because an electron volt is defined as the kinetic energy of 1 coulomb of charge accelerated in 1 volt of potential difference. The reason we make this change in units is because the electron volt will give us values that are in a more appropriate scale as we talk about dealing with energies of subatomic particles. Let's consider an example here. So one of the typical calculations we can see is that we could be asked, what is the energy of the average photon associated with green light? It could be any particular wavelength. We choose green this time. And we'll want to answer this in electron volts for now. So we're going to start with Planck's equation, E is equal to hf, remembering that h is a constant, so that's the 6.63 times 10 to the negative 34 joule seconds. But we're left with a second unknown, and that's frequency. So we consider what else we've been told. We know that the light is green, so that tells us the wavelength of the light. And from last week, remember that light travels at the speed of light. So our wave speed equation can be rearranged to get the frequency, which is the speed of light divided by the wavelength. The speed of light is 2.99792458 times 10 to the positive 8 meters per second. And a typical wavelength for green light is approximately 550 nanometers, and nano is the prefix of 10 to the negative 9. And I'm also predicting that we're going to need to make a conversion between joules and electron volts. Planck's equation is set up to calculate in joules, so we're going to convert it to electron volts as we do our answer. So setting up the equation, substituting for frequency, and substituting our known values along with our unit factor, we see that the approximate energy of a photon associated with green light would be 2.255595129 electron volts. And our limiting factor here is the precision of our wavelength of green light. We picked 550, so we'll treat all three digits as significant and we'll answer at approximately 2.26 electron volts. At this scale, when we're talking about energy, we typically assume that all of this energy is contained as kinetic energy of the photon. I want to assure you that our look at quantum physics is not going into the deep weeds and the newest extents of the field, and we're staying with fairly established quantum concepts. And in an effort to better understand some of this quantum theory, we're going to look at one of the experiments that helped establish quantum mechanics and our understanding of photons. This experiment was the photoelectric effect. In short, if we have light of different wavelengths incident upon a surface, we find that electrons can become energized and they'll behave in several different ways, which could include, depending on the surface, being ejected from the material. Classically, thinking that light is a wave and transfers energy in terms of watts per area, it would be expected that increasing the intensity of the light or allowing the light to shine for longer and longer and longer on the surface would eventually impart enough energy on an electron to eject it from the material. But this isn't what was observed. The quantum theory here observes that the intensity isn't as important to the effect of whether or not an electron is ejected, so much as the actual energy level. So even dim light at the correct wavelength can still eject particles. This ejected electron is referred to as a photoelectron, and physicists really needed to dig into why this phenomenon happened, that electrons weren't ejected at all intensities, and that electrons weren't ejected with more and more kinetic energy as we increased the intensity. So keep in mind, this photoelectron, when it's ejected, it has a mass. We saw that in our previous lectures, and it will have a velocity if it's ejected. So we're looking at the kinetic energy of the ejected photoelectrons. Let's look a little closer at that photoelectric experiment. Say we have some material, and in that material there's definitely some electrons, and we impart on it light of a wavelength of 700 nanometers. So as we saw earlier, that means that it's going to have a specific wavelength, which means that it has a specific color, and it will carry a specific energy of 1.77 electron volts. And no matter what intensity, so what brightness we shine that light on the surface, we see no emission. And no matter how long we leave it shining on that surface, again, we still see no emitted photoelectron. Which is odd. We would think that we are constantly sending energy at the surface. Eventually, we should, in a classical sense, energize an electron enough to jump off the material. But if we send lights of other wavelengths, let's consider 550 nanometers and 400 nanometers, so green and violet, we do see electrons leave this particular material. But when those electrons leave the material, we're not seeing kinetic energies or velocities that we would expect. Again, the classical theory was that if we increase the brightness of the light, green or purple, we should see more kinetic energy on the electrons that come from those lights. But that's not the case that we're seeing. Similarly, in between these wavelengths, we're not seeing particles get ejected in a continuous manner. So the energy here is being very, very quantized. It's got discrete gaps. To understand this, we need to look closer at the structure of the atoms in this surface. Our understanding of the atomic structure is governed by the Bohr model of the atom. Quickly reviewing this model, it's represented with a positively charged nucleus, which is surrounded by negatively charged electrons. Depending on the atom and its specific ion, we'll see a different number of electrons that occupy very specific orbits. These orbits each have their own energy levels that they can occupy. Now, it's possible for an electron to switch orbits, which means it must transition between different energy levels. For our next couple of slides, we're going to consider the hydrogen atom, and we're going to consider 5 of the levels for the electrons in the hydrogen atom. So in level 1, we have a binding energy of negative 13.6 electron volts. In level 2, it's negative 3.40 electron volts. Level 3 is negative 1.51 electron volts. And level 4 has negative 0.85 electron volts. And level 5 has negative 0.54 electron volts. To move from one level to another, we need to calculate the change in energy of the electron. So this is called an electron transition, and it's another one of our familiar change in calculations. So the change in energy means that we're going to take the energy of its final position and subtract from that the energy of its initial position. Let's look at 2 example transitions. Let's consider an electron that transitions from level 1 to level 3. So its change in energy is energy of level 3, subtract the energy of level 1, which is negative 1.51 electron volts, subtract negative 13.6 electron volts. When we subtract a negative, we end up adding, so we see that we have 12.1 electron volts of energy needed to go from level 1 to level 3. In the other example, let's consider going from level 4 to level 2. So the change in energy from 4 to 2 is equal to the energy it finishes at level 2 with, subtract from that the energy it started with level 4 with, which is negative 3.40 electron volts, subtract a negative 0.85 electron volts. And in this case, we see a negative 3.32 electron volts. So we have to consider what this is trying to tell us. Again, negative signs often lead to confusing situations. If we look at our drawing, as we see the values, they're negative. As we get a bigger negative value, that's a lower energy level. So to move from level 1 up to level 3, our electron must absorb 12.1 electron volts of energy. And to move from the higher energy level down to the lower energy level, then our electron must emit 3.32 electron volts of energy. This is a concept that you're going to need to take a little bit of caution with to ensure that you're considering our energy levels the correct way. Now let's look on a little more closely at what it means to absorb or emit energy. Let's look specifically at what increasing an energy level would involve. This involves photon absorption. Let's take our hydrogen atom and let's shine 4 different wavelengths of light on it. So we're going to impart on this atom a photon with a wavelength of 656.4 nanometers, another one with 486.5 nanometers, a third with 433.8 nanometers, and finally one with 532.5 nanometers, all representing the wavelengths, thus the color of our light. We're going to see if any of these photons would be absorbed by the electrons surrounding our hydrogen nucleus. To do this, we have to consider the possible transitions. While this isn't an exhaustive list, let's look at 3. We could consider an electron going from the first level to the second level, and that would require 10.2 electron volts of energy. And we could look at a transition from the second level to the third level, and we can calculate the requirement there as 1.89 electron volts. And a third possible transition is that an electron could jump from the second level, skipping the third level, and arrive at the fourth, and that would require 2.55 electron volts of energy. So these are several of the possible transitions. Now we have to look at the photon energies that we are carrying to see if any of them would cause those transitions. Remember, this means that we look at the energy of the photon, which uses Planck's equation, except for we're going to substitute for frequency. And we have to remember to convert the joules of energy to electron volts of energy. Let's look at that red photon. So H and C are constants. We've already seen what they are. I'm just going to plug in the wavelength and that unit factor for converting energy. And we see that the red photon carries 1.89 electron volts of energy. So if the red photon coming into our hydrogen atom managed to interact with an electron that was at the second level, then it would energize that electron enough that it would jump up to the third level. Let's consider the green photon, the one with 532.5 nanometers. I'm going to rush through the calculation here, but this photon carries with it 2.33 electron volts. Now, we've already seen from our possible transitions that going from 2 to 4 would require 2.55 electron volts, so we don't have enough energy to make that jump. We have too much energy to go from 2 to 3, and all our other energy requirements from level 1 are much greater than this, and all our transitions from level 3 are much smaller than this. And this is the important part of quantum physics. If a photon comes near an atom and it does not carry exactly the amount of energy that would cause one of the electron transitions, it won't interact with any of those electrons. It will continue and just pass right by. Now, if this happened to encounter a high level electron, then it might be able to eject that electron. But remember, especially for hydrogen, high level electrons are very rare. All of our electrons want to stay down near that ground level. Most electrons will be in the first state. This is that quantized phenomenon that makes quantum physics. Now, what I'm going to leave for you is, will the blue and purple photons be absorbed? And the answer is possibly. We mentioned that an electron at a higher energy level wants to come down to its base. So let's look at what that means as far as energy transitions. So again, using the hydrogen atom as our model, we could consider what happens when an electron transitions from the 5th energy level, jumps all the way down to the 3rd energy level. Here we see that it's a change in energy of negative 0.97 electron volts, which means it's giving up 0.97 electron volts. If we rearrange the wavelength equation, and again, remember that you'd have to do some conversion work here, we get a wavelength of 1,279 nanometers. This is well below the visible range, and it's in the infrared range. Let's consider a different example. Let's see an electron that is on the 2nd level and drops down to the 1st level. Well, we've already done this calculation. That's a change in energy of 10.2 electron volts. And again, doing our calculations, we would get a wavelength of 121.6 nanometers. This is well above the visible spectrum, and this is in the ultraviolet range. Let's look at a transition that's actually going to have an emission in the visible range. Let's go back to the 5th level, and this time let's drop all the way down to the 2nd level. So we do our calculation. We see that we have a change in energy of 2.86 electron volts. We use our rearranged Planck's equation to say that the wavelength is equal to h times c divided by the magnitude of the change in energy. A negative wavelength just wouldn't make sense here. So we input our constants for Planck's constant and speed of light. We divide by our change in energy magnitude, and we divide by our conversion value from our unit factor. And we get an answer of 433.8 times 10 to the negative 9 meters. Remember, 10 to the negative 9 represents the nano prefix. So this is approximately 434 nanometers. So we would get an emission of violet light. If you think back, if we would emit violet light on this transition, going the other way from 2 to 5 means that our previous example, the purple light, would be absorbed by that electron. Okay, with our understanding of energy levels of electrons and how light relates to that, let's go back to our consideration of the photoelectric effect. So we have some material, it has electrons. This time we're only going to shine ultraviolet light on it. So this is not in the visible spectrum and it carries a lot of energy. We have 12.41 electron volts of energy on every single photon in this emission. If we zoom in on this electron, remember it's associated with an atom. That atom has several energy levels that we expect to see this electron possibly at. And if we're able to eject an electron, the amount of kinetic energy it has is dependent on the energy level it was at. The energy levels we saw gave us the magnitude of the binding energy for each atom. So for the levels we have sketched, we would have binding energies of 13.6 electron volts, 3.4 electron volts, and 1.51 electron volts. We can calculate the expected kinetic energy of any photoelectron. Remember, photoelectron is our ejected electron. The maximum possible kinetic energy would be calculated by H multiplied by F subtract phi. Now, phi just represents those binding energies. And remember, H multiplied by F is our photon energy. So given a known substance and a controlled light source, we should be able to calculate the expected kinetic energy of a photoelectron. So what happens if we had light incident on an electron in the first level? So in that case, we are shining our 12.41 electron volt ultraviolet light on the hydrogen. And if the electron available is at the first energy level, we know that it has a 13.6 electron volt binding energy. And when we do that subtraction, we get negative kinetic energy. We see the binding energy is greater than the photon energy. We actually have no emitted electron if the only electron available is at that first energy level. There just simply isn't enough energy to be able to free that electron from its level. Let's look at a slightly higher energy level electron. So what happens if we have an electron at the third level and we shine the same light on it and it interacts? So we have 12.41 electron volts of energy incident on the electron. We subtract from that the 1.51 electron volts of binding energy, and we get a result of 10.9 electron volts surplus. So this is the maximum kinetic energy that an electron ejected from level 3 by a 100 nanometer light source could have. It doesn't matter how intense our light source is. Depending on the wavelength, that's what determines the amount of energy we're imparting. And this is the part of the photoelectric effect that classical physics couldn't explain. We only get those ejections based on the color or wavelength of light, not the intensity of the light. While that explanation was useful for us to understand what's going on with a photoelectron and the photoelectric effect, it's not typically the way in which we employ our understanding of this concept. The way we actually use this is that we will have a controlled applied ultraviolet light, and we choose ultraviolet because of how much extra energy it brings with it. And we'll have a detector that will measure for kinetic energy of a photoelectron, which means if we rearrange our previous equation as phi is equal to HF minus kinetic energy, we've detected the kinetic energy. We're subtracting that from the controlled applied ultraviolet light, And this allows us to calculate the binding energy of an unknown substance. So we're able to use an electron spectroscopy tool to identify unknown substance by comparing the kinetic energy of its photoelectrons to known sources. Each substance has its own binding energies, which means it'll have its own spectral pattern of emitted photoelectron kinetic energies. And we use that detected pattern to compare against known samples. In our early look at quantum theory, we saw that there was the photoelectric effect that was better defined by treating light as if it acted like a particle. At the time of its discovery, still many scientists believed the photoelectric effect was just a more nuanced application of wave theory. At that time, Einstein proposed that the photon would carry a momentum, and that could be calculated using Planck's constant and the wavelength. But experimental evidence of this needed to be sought. The Compton experiment found this. So the Compton experiment involved firing photons at other atoms, and at times what was seen was that the energy and the frequency of the photons would be unchanged when the photon transferred straight through the atom. But other times the photon was found to be off to the side, or it would have changed its direction of travel. When this happened, the energy or the frequency were changed as well. The important part here is that the amount of change could be predicted using the classical conservation of momentum approach to collisions. This was evidence that there was a momentum involved with the interaction that the photon had with the electrons of the atom. This Compton scattering supported the momentum theory, which means it supported the particle theory of light and further cemented the theory that we had to treat light with a dual behavior of wave nature and particle nature. One of the other consequences of supporting the fact of the duality of light led some scientists to theorize that if light behaved like a particle and had momentum, then possibly matter behaved like a wave. It was theorized by the scientist de Broglie that a matter wavelength could be calculated. So in this case, we see this as a probability. So if we picture an electron in the Bohr model, the true belief is that the electron's position has wave-like properties. We have areas of high probability of observing electrons and areas of low probability of observing electrons. And this is due to the fact that the electron has that slight oscillation movement associated with a wave. So de Broglie's matter wavelength can be calculated using the same equation that we saw previously. So the matter wavelength calculation for something like an electron would just be Planck's constant divided by the momentum of the electron. And because the electron has a mass that we were able to measure, we can calculate that momentum. Now, for particles with mass much greater than a subatomic scale, these wavelengths are extremely small and very difficult to scientifically observe. So we can see these wavelengths at the electron level, we have seen them at the proton and neutron level, but when you start doing calculations to try and determine what they would be for things the size of a baseball, they start to have a very, very small magnitude. What this means is that with a wave-like behavior, while we can use classical collision physics to describe what will happen with interactions on electrons, it introduces a probabilistic nature. Because the electron has a position, but we don't know that position perfectly, we could set up a collision and sometimes it'll occur and sometimes it won't. We're going to keep this in the back of our mind and we're going to move on and start to look at some of the applications of quantum theory to our investigations. We're going to take a closer look at the visual spectrum of light that we saw last week. Remember, the visual spectrum is a continuous spectrum where we have colors of light associated with different frequencies. Because light behaves both as a wave and a particle, we can calculate energy that particle would carry using the equation E is equal to hf. And remember that energy and the wavelength of the particle are inversely related, and we can also calculate that. So on our red end of our spectrum, we have low energy and wavelengths of approximately 700 nanometers. And on our blue end of our spectrum, we have high energy with wavelengths of approximately 400 nanometers. So what we're going to look at now is the light that's put off by certain substances, the emission spectrum, and the light that passes completely through certain substances. And we refer to that as the absorption spectrum, and we're going to look closely at these in their explanation to understand why they're referred to as these things. Now, when we complete some spectophotometry, this is kind of a good sketch of what we're looking at. So we begin with some sort of high-powered source, and this source will put out white light, which is light of all wavelengths. And then we shine that light through lenses and our substance. Now, the lenses are used to spread the light out so that it covers all of the substance that we have, and then focus the light back together again so that we can properly refract it. Now, as the light passes through our substance, as we saw before, some wavelengths are absorbed based on how much energy they're carrying and the interactions they have with electrons in the substance. After traveling through another lens to refocus, a slit to begin the expansion progress, and a lens and a prism to refract the light to separate the wavelengths, we would be able to observe all of the wavelengths that were able to pass all the way through our sample. We're going to bring in that image of the absorption spectrum. Now you'll see here is we have this visible spectrum of light, and this is what we would observe at the far end of our spectrophotometry. And you'll notice that there's black lines all through this. These are our missing wavelengths of light. This is what we're referring to when we're talking about the absorption spectra. Each of these black lines are spectral lines corresponding to an energy level that our substance was able to properly absorb. You should recall that when we talk about absorbing energy associated with wavelength of light, we are thinking of a nucleus and its energy levels for its electrons, and that if it was able to absorb a photon, it could take an electron from the first energy level to the second, or the first to the third, or the first to the fourth. This was the transitions associated with absorbing a photon. After some time, the electrons at the higher energy levels will want to fall back to the lowest available energy state. And you'll see here, represented by all the pink lines, is that there are many more possible transitions from higher levels to lower levels than there are from lower levels to higher levels. This is because when electrons are stable and haven't been excited, they often want to be at that lowest level. So there aren't electrons in the third energy band to be excited up further. Because of the tendency of electrons to remain in the lower levels when they're not excited, and then excite up to the highest levels, and then the possibility that they don't fall all the way back down to the lowest level immediately, means that there is often a greater emission spectrum than there is absorption, because there's many more variety of emissions that could happen. Let's bring up that emission spectrum again. So here, this emission spectrum is bright lines among a noisy but dim background. So we note that it's not a perfect sample. We still get some light that passes through to our sensor. Now, the fact that emissions are often delayed is what we're going to talk about here. But first, note that every time we have an emission that is not directly associated with a previous absorption, that emission will be at a longer wavelength because it's at a smaller energy. So we could have gone from 1 all the way to 4, takes a lot of energy in, but when we go from 4 back down to 3, we're only emitting a small amount of energy, so we would have a longer wavelength. Let's go back to that delayed effect. The delayed effect is referred to as fluorescence. So fluorescence is the emission of energy at a delayed point in time after an excitation. We have several different types of fluorescent reactions, but when we talk about emitting an energy, we may use that word fluoresces, instead of emits. Let's take a moment to look at a spectra example, albeit a fairly simplified one. If an ultraviolet, that's a 350 nanometer wavelength, is absorbed, how much energy was absorbed? So part one, we have our wavelength, 350 nanometers. Remember, we have our energy equation, E is equal to Planck's constant multiplied by the frequency. And we also know that because we're dealing with light in the electromagnetic spectrum, we have C is equal to wavelength times frequency. Rearranging the second equation and substituting it into the first, we find that we can calculate the energy from Planck's constant, the speed of light, and the wavelength we were given. So plugging in our values of 6.62607,004 times 10 to the negative 34 joule seconds, and the speed of light at 2.99792458 times 10 to the 8 meters per second, and dividing that by 350, but instead of nano, we'll write times 10 to the negative 9 meters. And calculating, we get 5.67555498 times 10 to the negative 19. If we consider our units, we have seconds canceling with the per second. We have meters on the top and meters on the bottom. So luckily, our energy comes in units of joules. We only have two significant digits here, so this is approximately 5.7 times 10 to the negative 19 joules that were absorbed with this one wavelength. Let's look at part two. If the atom then fluoresces 4.174 times 10 to the negative 19 joules of energy, what is the wavelength and color of the emitted photon? So in part 2, we're given energy. I'm going to rearrange the equation we created in part 1. So now it says wavelength is equal to Planck's constant multiplied by the speed of light divided by energy. We're going to substitute those same two constants up top. We are going to divide by our energy of 4.174 times 10 to the negative 19 joules. And if we plug this into our calculator spits out this value, 0.000000475. Remember, we're talking about wavelengths here, so while this would be a scientific notation value of 4.75 times 10 to the negative 7, I'm going to move my decimal place two further places so that I can say this is 475 times 10 to the negative 9 meters, which is approximately 475 nanometers. And if you consult the chart on your formula sheet, this would be blue light associated with a wavelength of that length. Let's look at how we apply the fluorescence effect. Now, if I shine some ultraviolet light on a piece of DNA, the spectral that is emitted by the DNA, or the spectral that makes it through, is actually quite complex. And a lot of the substances we look at, especially when it comes to DNA or organic compounds, are very similar spectrally. So it's difficult to use the fluorescence effect to determine different substances directly. Instead, what we do is we pick dyes or dye agents that have a specific behavior around certain substances. So a dye agent will bond to some substances, but not others. Then, when we expose the dye agent to ultraviolet light, the dye that has bonded to the substance we want to know of its presence will absorb the ultraviolet light, and then later, it will fluoresce light out. Now, because it fluoresces light at a longer wavelength than it absorbed it, we'll actually see it'll be in the visible spectrum instead of the ultraviolet spectrum. And this fluorescent glow would then identify the presence of our substance of interest. Even the absorption spectral analysis is difficult to pinpoint. To date, we keep doing examples that involve one photon. In practicality, it's difficult to isolate and observe just one photon. A 100-watt bulb emits approximately 100 billion photons every second. So that's 1 times 10 to the 20 photons per second. When we think about the function of what we've looked at in the past few examples, it's happening many, I think you get the point, times per second. So what we want to actually look at is the percentage of these that are absorbed, and that's going to help us get an idea of what kind of interactions are happening. So in spectophotometry, what we do is we have a substance or a sample, and we're going to shine an incident light on it. Some of that light will make it through, but some of it won't. But the light that makes it through is referred to as a transmitted light. It's been able to transmit through the substance. Rather than trying to understand the individual energies that have transferred through the substance, we use the amount of energy that transfers through the substance to give us an idea of sometimes what the substance is and other times the concentration. Recall from earlier in the lecture, we have that probabilistic approach to interactions between photons and electrons. This is another reason why trying to consider this as firing one photon through a source doesn't work, because there's that possibility, or it's more likely, that the photon goes straight through the atom and the substance and doesn't interact with any of them. So by using the spectophotometry and the comparison of intensities, we deal with that low probabilistic interaction that we've just talked about. This comparison of the amount of intensity that gets through a substance to the amount of intensity that was incident on the substance is called transmittance. And we have the equation T is equal to IT over IO. So T is the transmittance. The IO on the bottom is the intensity of the incident light. And for this example, we're going to measure that in photons per second. And IT is the intensity of the transmitted light, again measured in photons per second. I think you may notice here that if we're measuring in photons per second and photons per second, that T will not have any units. It's just a ratio. And the other thing is that because the light that gets transmitted through will always be less than the light that was incident, unless some odd reaction happens, this value will also always be less than 1, or should be less than 1, and as it's a ratio comparing something that is always smaller on the numerator to something that's always bigger on the denominator. So now we'll look at an example, and again, we don't typically measure intensity in terms of photons per second, but this example illustrates what transmittance means. So if a spectrometer beam emits 140 times 10 to the 18 photons per second, and we detect 56 times 10 to the 18 photons per second after passing the light beam through the analyte, what is the transmittance and its percentage? So transmittance is equal to the comparison of intensities. The intensity that we detect after is the 56 times 10 to the 18. The intensity of the incident, which is our denominator, is 140 times 10 to the 18. Our magnitude and units will cancel out here, so we're really comparing 56 to 140, and we get back that we have a transmittance of 0.4. This is a ratio, so if we multiply it by 100, this tells us that roughly 40% of the light makes it through the analyte substance. With a transmittance of 0.4, we're able to consider something more important, the absorbance, which is the amount of light that the substance, the analyte, was able to block. Now we have this equation. A is equal to negative the logarithm base 10 of our transmittance. The absorbance actually increases exponentially with some feature. So we need to have this logarithmic function to make this a more linear relationship. We need to take a quick review. I'm not sure how comfortable you are with logarithms, but you need to understand that a logarithm answers the calculation. Which exponent, a here, do I need to raise the base, 10 in our case, to in order to have a result of t? This is really just a rearrangement of the equation 10 raised to the exponent a is equal to t. And using logarithms is our way of applying something similar to algebra to solve for that value of a. Remember, in our application, t is always less than 1. So in order for us to have the result of this exponential equation, our exponent will always be negative. So we develop our absorption formula with that negative in front of the log to make sure we always get a positive value for absorption. So using our previous example, we see that the absorption will be equal to negative the logarithm base 10 of the 0.4 transmittance. And if we plug this into our calculators, your calculator should have a log button. And note how it doesn't have a 10. Calculators always assume that the base logarithm you're working with here is 10. If you need to work with a base of e, remember that's the ln button right beside log. But we'll be using log. So we press the calculator button, have log of 0.4, and we see that it gives us a negative value because I forgot to type in the negative. So we can write down that our answer is 0.397940008. And while significant digits with exponents is a little tricky, we'll just keep 4 of those digits for now. So this is approximately 0.3979. Let's consider an example for Beer's law. We know that the molar absorptivity of an analyte is 6.27 times 10 to the 4 liters per mole centimeters, and the transmittance through a 1.2 centimeter test tube is 0.6. What is the concentration of this substance? Well, recording what we know, we have an epsilon value, the molar absorptivity of 6.27 times 10 to the 4. Notice the connection here with the units. Liters over top of moles and centimeters is the same as moles raised to the -1, centimeters raised to the -1. We have a length of 1.2 centimeters, which is okay. So we take a look and see that our centimeter length lines up with the per centimeter molar absorptivity. We were told there's a transmittance of 0.6, and we're trying to find the concentration. We use our two formulas that we have here. A is equal to epsilon times L times C. And at the same time, A is equal to negative log base 10 of T. We can set these two equations equal to each other. We can rearrange for the concentration, and we can substitute our values. So we're going to calculate negative log base 10 of 0.6 divided by 6.27 times 10 to the 4 divided by 1.2, and we see we get a result of, and again we have to be careful, if we look at our result, this is 6 total zeros, so we need to have 2.94 times 10 to the -6. If we consider our units, this will be moles per liter. This lecture, we began our look at quantum physics. So we examined the quantized nature of the interactions between electromagnetic radiation and matter, so light sources and atoms of substances. To do this, we reviewed the Bohr version of the atomic model and the energy levels associated with electron orbits that are possible for each atom. We looked at calculating the relationship between photon wavelength and the electron energy levels, and we considered the application of these concepts in quantum mechanics to spectroscopy. Investigated further applications of quantum physics. We examined the ways we use the quantized behavior of light to examine substances. We saw that this often relies, though in different ways, on the measures of the absorption and emission of energy for each substance. Sometimes those are precise measures, and other times we are just looking for the effect to exist itself. We applied this understanding of absorption and emission to investigative techniques, and we even introduced a new law, Beer's law, and connected it to a method of non-invasive concentration analysis.